Melamine-doped titanium dioxide as a perspective photocatalyst for hydrogen evolution. Hydrogen as a clean energy source has excellent prospects. Getting hydrogen from the photocatalytic decomposition of water under the action of UV and visible light is generally considered the most straightforward and cheapest technology for hydrogen production. But main problem is finding the most efficient photocatalyst for this process. Titanium dioxide is the most efficient and promising because of its electronic properties, non-toxicity, chemical inertness, and low cost. But it has some disadvantages, and the main disadvantage is it absorbs only a tiny fraction of solar radiation, about 3–5%. To increase the catalytic efficiency of titanium dioxide, researchers use that way as modification. And melamine is a promising carbon and nitrogen source for the titanium dioxide modification. That is why our work aimed to obtain and characterize melamine-modified titanium dioxide-based photocatalyst with a further study of photocatalytic activity in the direction of hydrogen generation from water using solar energy. For sample preparation, we used Sol-Gal method for the undoped titanium dioxide preparation. The titanium oxide, citric acid, and glycerol were mixed to obtain uniform message room temperature and further concentrated at 500 degrees centigrade for 2 hours in the presence of air oxygen. The samples of melamine-doped titanium dioxide were obtained using the same mixture, but with the additions of melamine, 4 and 8% before the heat treatment. After cooling, the powders were titrated until smooth. The 4 and 8% melamine-doped titanium dioxide samples were labeled as 1 m titanium dioxide and 2 m titanium dioxide, respectively. These samples were investigation by different methods. You can see this method on this slide. Photocatalytic hydrogen evolution was studied in a cylindrical glass temperature-controlled reactor. In the experiment, the prepared photocatalyst was dispersed in an aqueous solution containing ethanol as electron donor, and co-catalyst was added into this mixture. The reaction mixture was degassed before the light irradiation using a vacuum pump. The suspension was irradiated using a high-pressure macular lamp under constant stirring with a magnetic stirrer. The gas phase composition above the solution was evaluated chromatographically every 30 minutes. The diffraction peaks at 2 theta equals 25.6, 37.8, and so on, corresponding to anatase, and one small peak at 2 theta equals 27.4 that correspond to the rutile crystal structure. The rutile content didn't exceed 12%. The overall X-ray D intensity from M titanium dioxide powders decreased compared with that from undoped titanium dioxide. The decrease may occur also due to the titanium dioxide lattice deformation or reduction of crystallized size after the modification. Indeed, we can see increasing of lattice parameters and molecular unit volume of titanium dioxide, and such modification prevents the growth of crystallized during heat treatment. We also investigated these samples with Raman spectroscopy. We use the spectroscopy to determine the stoichiometry and the size of nanocrystallize in the prepared titanium dioxide. Besides, we use UV-vis absorption spectroscopy to measure the band gap of these samples. It was established that the band gap for titanium dioxide is 3.27, for 1M titanium dioxide 3.14, and for 2M titanium dioxide 3.32. And of course, we investigated the water splitting reaction in the presence of these samples under the light illumination, and the photocatalytic decomposition of water into hydrogen and oxygen requires the presence of a photocatalyst and electronically excited semiconductor with a band gap less than energy of the incident light. As we found, the melamine-doped titanium catalyst showed more than 2 times higher activity than undoped titanium dioxide. First, it was due to the decrease in the particle size. The rate of volumetric recombination of photo-induced charge carriers also decreased significantly. They reach the surface much faster than the average time of volume recombination. And the second reason is the narrowing of the band gap. We have some conclusions. A set of photocatalysts based on titanium dioxide doped with melamine was successfully synthesized to obtain the high effective photocatalyst for hydrogen generation. It has been found that titanium dioxide modification with melamine decreases crystallized size and changed in the latest parameters of titanium dioxide. The stoichiometry of modified samples deteriorates, indicating the existence of additional oxygen vacancies in the doped samples. Changes in the oxygen content may be accompanied by the appearance of titanium 3+ energy levels in the forbidden band of titanium dioxide. The enhanced photocatalytic activity of 1M titanium dioxide towards hydrogen production in the direction of water splitting would appear to be more than 2 higher compared to unmodified titanium dioxide is mainly attributed to the narrowing of the band gap and increased number of surface active sites, and a decrease of photo-induced charge carriers recombination rate due to the decreased particle size. This study suggests that the proposed simple way for titanium dioxide modification with melamine can be used to obtain new materials with improved activity of hydrogen production and industrial wastewater treatment under the action of UV and visible light for creation of green energy and clean environment. So, thank you for your attention.